Okay. Good morning, everyone. We'll start our day with our first keynote speaker. So I'm going to quickly introduce Kovid Goyal. Kovid is going to be our first speaker for the day. He's the creator and ongoing maintainer for dozens of Python projects with multiple users across. Most prominently, he's working in Calibre, the ebook management program, and Kitty, the GPU accelerated terminal. While many of his Python projects are focused over speed, for example, the HTML5 pacer, which is 30 times as fast as the Python alternatives, or Kitty, which is the best-in-class performance despite being written partly in Python. So can we have a huge round of applause for Kovid? As we start the keynote with the first keynote speaker, a quick request is we will have question and answers towards the end of the session. So again, welcome on stage, Kovid. This is the clicker. You can just point towards the center.
Can this be made full screen? Oh, okay, never mind. Okay, hello everyone, good morning, welcome to PyCon. Let me start by thanking the organizers for inviting me to give you this keynote. It's a really well-organized conference and I'm sure you'll all have a good time. Okay, so my name is Kovid Goyal and I'll be talking today about making Python programs fast. Keyword being fast in yellow. So I've been writing Python code for about 20 years. My very first Python program was a little desktop widget for the K desktop environment, which used to show how much email you have in different folders. Now, this obviously wasn't performance focused, but it's where I started my Python journey, and I've been writing Python code every day ever since. So my first exposure to high performance Python was when I was doing my PhD, which was in theoretical physics, and I had to do some numerical work, and that was in Python. And I decided that I needed to make it perform well enough. I mean, my first attempt at it would, each sort of iteration, each time I ran the program, it would take 8 hours. And then, I had to wait for the results and then tweak things and then try again. So since then, I've been focused in many ways on making Python fast. So Python has a lot of advantages. It's dynamic, it's flexible, it's easy to use, but it is slow. So, I'm going to be talking about tips and techniques to make it fast today. Let's hope this works. Okay. So what's the need for speed? After all, if you've chosen Python as your primary programming language, then performance is not your most important criteria. Well, it starts with single core performance has flatlined. Thanks to the end of Dennard scaling, CPU clock speeds are stagnant. If you're running code on a single core, it doesn't go any faster. So we can't rely on hardware advancements for speed. We have to actually make our code faster. So performance is not just about being fast. It's also, when you make something faster, typically what you're doing at a low level is asking your CPU to execute less instructions. Write a smarter algorithm, maybe do some optimizations, whatever. And so this translates not just into faster performance, but also into energy savings. And we're not talking about a lot of energy here. We're not going to single-handedly save the world from global warming. But in some contexts, it can be useful, especially on portable devices where it affects battery life directly. Or if your program is running on thousands of servers, it'll lower your bills. Okay. Let me stay on this side of the stage so the clicker works. So users love performance software. Everything else being equal, users will always pick the faster program of two. They like software that has low latency, that responds instantly, that has high throughput. It finishes its tasks as quickly as possible. And performance software sort of forms a platform on which further things can be built easily. And finally, most importantly, writing, at least for me, writing performant code is a fun challenge. So Python puts up a lot of roadblocks for you in the way of writing performant code because it itself is not highly performant. So in that constrained environment, being able to write programs that are fast nonetheless is a sort of fun intellectual challenge. And if you're like me, you'll end up spending weeks, months, years of your life solving that intellectual challenge. Okay, is it even possible? Now, obviously, I'm here to talk about making them fast, so the answer is yes. This is a violation of Betteridge's law. But as I said, Python is slow. Typically, the same algorithm, the same code running in Python will be about a factor of 100 times slower than the equivalent code running in compiled form, native instructions. So there's a lot of work going on in the Python ecosystem to make Python faster. For example, the upcoming experimental just-in-time compiler, the no-GIL effort, and so on. But at least from what I've seen so far of them, they are not going to put a significant dent in that 100x slowdown. You're still going to have to resort to doing what we can at an application level to make our software fast if it's written in Python. So I'm here to tell you that it is possible, and as an illustration to motivate it, I'll talk a little bit about one of my projects, Kitty, which is a terminal emulator. So here you have a table of some well-known terminal emulators. They're written in compiled languages. You can see in the second column they're written in C++ and Rust. The third column tells you the throughput that they achieve. That's how fast they process data and display it on the screen. So you see performance is roughly the same. It's about 50 megabytes per second. Now, would anyone like to guess where my terminal emulator project, which is written partly in Python, is? Well, it's about twice as fast as the next fastest terminal emulator. And the secret to that is that it's not just Python, it's also C. And that's going to be the theme of my talk, that you can make Python programs fast by writing just a little bit of C. The key is that it's a little bit. If you write too much C, then you're basically writing a C program and you have all the problems of C, crashes, memory corruption, et cetera, et cetera. But if you write it in a constrained fashion, you write so in most programs, 90% of the code is UI, it's business logic, it doesn't need to be fast. There's very little code that actually needs to be fast, and it's just that you focus on and rewrite in C or some other performance techniques that I'll be discussing. Before I go on, let me say that this is going to be a slightly technical talk. There's going to be actual code on the screen. And so if anybody has doubts or questions, you can ask me questions after the talk, or later you can catch me and I can help clarify something that you don't understand. So one slide about Kitty itself. So as I said, it's a terminal emulator. For those of you who don't know what a terminal emulator is, it's basically a software program that parses a stream of input data, a stream of bytes, and converts that into text and images and output on the screen. So my goal in writing Kitty was to make terminals a powerful platform, a platform for powerful software. So, I've innovated many features such as support for images, support for input events, and so on. I originally started Kitty as a project for my own use, and in doing so, I realized that the terminal ecosystem was very stagnant, and I wanted to sort of move it forward. And I realized that in order to do that, it would be necessary for Kitty to perform really well. Because if it was slow, if it was a pure Python program, it would be slow. No one would be willing to use it. So that's kind of the motivation for why Kitty became fast. There's a cute little kitten there. Sort of the key thing here is that Kitty is written mainly in Python. Python is used for its UI and control. Users can write little Python programs called kittens, which integrate with Kitty and allow you to customize it and make it more flexible. So that's the advantage it gets from being written in Python. It's dynamic, it's customizable, it's flexible, but at the same time, it's also performant. So the way it achieves its performance is it writes the performance critical parts of the code in C, and it offloads rendering to the GPU so that it's as performant as possible. So as I said, terminal emulators basically process a bag of bytes. You give them a stream of bytes, which consists of text, and embedded in that text is control codes. So for example, you'll have an escape character, which is 1B in hexadecimal, and then followed by some control data. That control data tells the terminal emulator how to format the text and how to output it on the screen, move the cursor around, et cetera, et cetera. So the job of terminal emulator is basically to parse a stream of bytes, extract the text, extract the control codes, and following the instructions of the control codes, display that text on the screen. Seems simple enough, and in some ways it is. But in some ways, if you want to make it performant, it's not quite that simple. So a little bit of history. I originally started Kitty, as I mentioned, for my own personal use. So about 8 years ago, I was using GVim, and I wanted to switch to terminal Vim because the rest of my workflow was based on the terminal. But I wanted squiggly underlines, the underlines you get under misspelled words or syntax errors. And no terminal at the time had that feature. And so I wrote my own and added that feature, and today this feature is available in most modern terminals and most editors. And I indeed use Vim in the terminal with squiggly underlines. Okay, so that's enough about Kitty. I'm here to tell you about techniques you can use. And I'm going to be doing that with a series of case studies. So these are little examples that show how you can speed up small tasks that may be performance critical in your particular program. And these examples are chosen to be simple so that I can just talk about them in a keynote talk. They're not too technical, but nonetheless, there's going to be some code. And the exact examples are not important. The idea is to motivate to you that it is possible with a little bit of elbow grease to make your Python programs fast. So the first case study is base64 encoding. Now, base64 encoding is basically a way of representing binary data in text format. So you have as input arbitrary binary data, bytes like, so for example, in this we have the word encoded, which is your input. And in base64 encoding, it's split up into groups of 3 bytes, and each 3 bytes becomes 4 characters. So ENC becomes RW5J, ODE becomes B2RL, and so on. And of course, actual real-world input may not be a multiple of 3 in size. So when that happens, you have some padding bytes added to the output. So for the ensuing discussion, I'm going to neglect the case of padding bytes. I'm going to assume my input is always a multiple of 3, just to make the algorithm simple. Okay. So base64 is used widely all over in communication. It's used in emails. It's used in web pages. In fact, this very presentation is a single HTML file with all its images and resources embedded in that HTML using base64 encoding. All right, so before we get started with writing a Python base64, let's establish a baseline. What sort of performance can we expect? What are we looking for? Can we do better? So the baseline is established using the venerable base64 command, which is available on most Linux and Mac OS machines. It's written in native code, compiled code. And here we benchmark it. So what I do in the first line is write out 1 gigabyte of random data into shared memory. The reason for using shared memory is it removes disk I/O from the benchmark. And then I use the hyperfine utility to run base64, encoding that previously saved data. And the result is that on my laptop, I get base64 encoding at about 1.6 gigabytes per second. So that's kind of what we want to aim for, 1 gigabyte per second encoding. So let's start with a naive Python implementation. And again, if there's something you don't understand, please feel free to ask me at the end of the talk or afterwards. It's kind of difficult to explain code in too much depth in the middle of a talk. So this is a naive Python implementation. What we do is we take as input a Python bytes object, and we output a Python bytes object. A simple enough function. As I said, base64 works in groups of 3 bytes. So we loop over the input in groups of 3 bytes. You see we calculate this triple, which is the first input byte, the second input byte, and the third input byte. So this is basically, base64 happens in 24-bit groups. And using those 24-bit groups, we reinterpret the 24 bits as 4 groups of 6 bits each. And each of those we look up in a base64 table, which is this base64 chars here, which is just a Python byte string. And looking it up, we get the output, 4 bytes of output, and we loop over this. Okay, so this is a really simple algorithm, 10 lines of code. So it serves as a good sort of case study for us to understand some optimization techniques. So let's see what the performance of this basic implementation is. It turns out it's 1.2 megabytes a second, which is 1,000 times as slow as the base64 native binary. Now, I said on one of the introductory slides that you can expect about 100x slowdown with Python code, and this is 10 times worse. So that indicates that there's something wrong with this naive implementation, and we can do better. So let's look at that. So let's add some street smarts to our naive implementation. We observe that in the naive implementation, there is this line where we are slicing the input bytes object so that we operate on 3-byte chunks in each loop iteration. Now, for those of you who are familiar with Python bytes objects, you'll know that slicing a byte object essentially creates a copy. So say we had 1 gigabyte of input. On each loop iteration, we are copying that 1 gigabyte minus 3 bytes to a new location in RAM. And this is obviously slow. So this is a trivial and obvious improvement we can make. We cannot do this copying. So it's just a simple 2-line change. Instead of a while loop, we make a for loop and we use an index j, which advances in groups of 3, and we calculate the triple in exactly the same way, except that we use j instead of 0, 1, 2. And this simple 2-line change gives us a 5x improvement. We are up to 7 Mbps. Now, obviously, this is a big improvement, a simple change. If all you're doing is optimizing pure Python code, this would be a great result. But we can do better. We want to reach 1 gigabyte per second. So before we go on to doing that, a small detour about a very useful Python class called memory view that many people don't know about. It's in the standard library. It's basically something that's really useful for working with binary data. If you're doing some kind of pure Python algorithm on binary data, please use memory view. So what memory view is basically a view of the memory in your computer. You can think of it as a pointer and a length. So if you have an input bytes object, you can create a memory view by just calling memory view like that. And the important feature of memory view for us is that slicing doesn't create copies. So what this does is this slice here, it's operating on a memory view now. And it, instead of copying, it just creates a new memory view object with an offset pointer and length. So we can get rid of those indices, go back to a while loop, and we can use this for both the input and the output. And this is nice because if you don't have to keep track of indices, there are less chances of you making, off by 1 errors, which are sort of the hardest errors to debug. So you can sort of get back to a nice Pythonic way of doing things without sacrificing performance. You can see that the rate is almost the same. From 7 Mbps, we went down to 6 Mbps. But we gained some code elegance and making the code easier to maintain in the future. For such a simple function, obviously, it doesn't really matter. The loop with indices is fine. But in more complicated code, this can make a difference. Okay, so the point here is, please be aware of memory view. If you are working with binary data in Python, use memory view wherever possible. Okay, so the next obvious sort of thing is, can we use parallelism? Nowadays, computers have CPUs with multiple cores. They're just sitting there doing nothing, so let's use them. So this series of slides about parallelism, I'm going to parallelize the base 64 algorithm, and it's going to serve as an illustration of how easy it is to do parallelism in Python, so that for more complicated real-world problems, you may be able to use it in your code. So the first step is to rewrite our base 64 encoding function, so that rather than taking a single input object and outputting the output, we instead take 2 memory views. The first is the input, and the second is the output. So we'll do the same encoding algorithm, but we'll write our output to the specified out object. The reason for doing this is that we'll split up our input and output into chunks, and each worker process will work on one of those chunks. And so therefore, you need a function that allows you to specify the output chunk, otherwise there would be an extra copy. So we are avoiding that here. Okay, sorry. So the rest of this function is exactly the same. It works with the while loop on memory views. Now we need a couple of additional functions to make this parallel. And the first is the chunk function, whose job is you give it an integer, and it gives you the input and output chunks corresponding to that integer. So supposing you're splitting your workload into chunks of 1 megabyte. When I is 0, it will give you the first megabyte of input and the first little more than a megabyte of the output buffer. It's 4/3 of the input. So the second, when I is 1, it will give you the second megabyte and so on. So it's a really simple function. It just does a little bit of maths and calls the parallel encoding function with the calculated input chunk and output chunk. Now the actual implementation is called parallel encode, and it's just 2 lines. What it does is takes an input bytes object and outputs the final encoded output, just as our original function did. The way it works is it uses a pool object, which will be a pool of workers that we again get from the Python standard library. I'll talk about that in the next slide. And it calls the map function, which basically just calls chunk with I ranging over the number of CPUs on your computer. So really simple, 2 lines. And once chunk is done writing the output, it returns it as a bytes object by creating a copy. This final copy is sort of unavoidable because output here in my implementation is a global. Okay, so let me just talk a little bit about creating a pool. So we have the nice multiprocessing module in the standard library from which you can import the pool class and the shared memory submodule. So what is shared memory? Shared memory is basically an area of RAM that is given a name and a defined size, and unrelated processes can connect to that shared memory and read and write it, each of them to the same shared memory, so that the master, the main process, finally has a view of the output data that all the worker processes have worked on. So we create it really easily. You use shared memory, you call the constructor, you say create true, and you specify the size. For us, the size is the input size plus the output size. The input buffer is then the first half, and the output buffer is the second half of our shared memory. Now, in the worker processes, we need to set up and connect to the shared memory. So we do that with this connect to SHM function. All it does is, again, call shared memory, but this time without create equal to true. Instead, you pass it the name of the shared memory, which Python generates for you. You don't have to worry about the details. And then you just recreate the input and output buffers in the worker process that refer to that same underlying shared memory. And that's it. You just create the pool that we used in the previous slide with passing it the number of workers you want, which is the number of CPU cores, and a reference to this setup function, which sets up each worker process. And so that's it with just these couple of slides of extra code. We have a parallel implementation of base64, and let's look at how it performs. So its rate is 4 times the rate of our previous implementation. It's almost 30 megabytes per second. Of course, the actual multiple you get depends on the number of CPU cores you have in the machine you're running. But the point is that you expect it to scale roughly with the number of CPU cores. So here we've gone up to 20 times the performance of the naive Python algorithm. But it's still 50x slower than native. So, and in some sense, parallelization is cheating because you're not actually making your code faster, you're just farming it out to more CPU cores. And that uses the same amount of energy, actually more, because there's some overhead of message passing between the cores. And you prevent those cores from doing other useful work. They're just busy base64 encoding. So at least for base64 encoding, parallelism is not really the answer. You don't want to achieve speed with that, but depending on your problem domain, depending on your individual program, parallelism might work well for you. So you should be aware of it as one of the tools in your toolkit. And the Python multiprocessing module exists just to make this relatively painless. And with the upcoming no-GIL work in Python, it should become even easier. You can use threads rather than processes. So let's now try to match the performance of the native base64 executable. Now, Python's performance superpower is C code. Python is really easy to integrate with C code. And let me say here that it doesn't have to be C. It can be C++, it can be Rust, it can be something else that compiles to native code without a runtime and exposes a C API. I personally prefer C, so I'm going to be using C in my examples. So as I was saying, Python's performance superpower is C code. You can write relatively small amounts of C and achieve large performance gains. Now, for those of you who are familiar with the Python standard library, you'll be wondering why I didn't just use the standard library base64 module. The reason for that is because this module is written in C. So I wanted to first explore the pure Python implementations. But yes, in the standard library, there is a base64 module. From that, you can import the base64 encoding function. And you can see that if you benchmark this, you'll end up with a rate that's of almost the same as the native base64. We are at 1.3 gigabytes per second. So are we done? Few. Is that all we need to do? Import one function from the standard library? Well, unfortunately not. So just like Python's performance superpower is C code, its Achilles heel, its weakness is standard lib bit rot. So there's a famous saying that the Python standard lib is where code goes to die. It's actually possible to do much better than both the Python standard lib base64 and the native base64 executable. So let's see how we can do that. And the answer is you're writing our own C code. So this is why this is sort of a motivation for why it becomes important to be able to add a little bit of C to your Python programs. Okay, so before I describe that, a little bit of a detour about something called SIMD. Now SIMD stands for single instruction, multiple data. Now what that means is it's a set of CPU instructions that operate on multiple bytes or multiple bits at a time. So in the classic base64 algorithm, you saw that we operated on basically 3 bytes at a time. We read each byte, we calculated its contribution to the triple, and then we output again 1 byte at a time. So with SIMD, instead what we do is we create a vector of multiple input bytes, and we process them all at once with one CPU instruction and output, well, not one CPU instruction, but a handful of CPU instructions. And we output the output encoded data into another vector all at once in parallel. But this is parallel on a single CPU, and it's very energy efficient. This parallelism is implemented in hardware, not in your code. So SIMD instructions, because of legacy reasons, can operate on different sizes of input. The common ones are 16, 32, up to 64 bytes at a time. So you can expect, speed ups on the order of 10 to 20 to 30 to up to 60 times, depending on your algorithm and what the overhead of the SIMD process introduces. Okay, so base64 again operates in 3 byte chunks. Each 3 bytes of input becomes 4 bytes of output. So now we want to operate on multiple 3 byte chunks. So what we will do is we load up the multiple 3 byte chunks into a SIMD register, which remembers up to 64 bytes in size. And we perform some calculations on it using SIMD instructions. And finally output our base64 into another SIMD register with, say, multiple groups of output in it. So at the moment, I'm not going to describe the SIMD algorithm. If at the end of the talk, depending on how much time I have left, I might tell you about that. Or you can catch me later in the breaks, and I'll tell you about it. So for the moment, I'm just going to use a library, something called aclomp base64. It's available on GitHub. It implements all the SIMD algorithm for us. It works with all the different types of processors out there. It's a nice library, and for our purposes, we are interested in one function from it. It's base64 encode. All it does is it takes your input data, which is a pointer to some memory, the size of the input, and the output data, output buffer, which is again pointer to some memory region, and the size of that memory region. And it returns in that same size, the size of the number of bytes it actually wrote. So now what we want to do as Python programmers is write a minimal amount of C to make this function available to our Python code. Okay? So let's see how we do that. So the answer is the Python C API. Now many people over the years have told me that they find the Python C API extremely intimidating, difficult to use. C itself is obviously has a lot of foot guns. It has pointers, it has lengths, it has undefined behavior, and so on. But for our purposes, we are writing very little C. It's concentrated, it's focused, It's easy to audit. It's easy to ensure that it's bug-free. I know saying that something is bug-free is famous last words, but at least practically, I have found that writing these small bits of C is actually quite robust in a larger Python program. Okay, so how do we make our simd base64 function available to Python? So we need to wrap it in a wrapper that interfaces between the Python types and the C types. So let's call this wrapper function pybase64. It takes two arguments. The self, which is familiar to all Python programmers, it's the self object, or in the case of C, the C API, it can be either an object or it can be a reference to the module in case the function is a top-level function. But we don't care about self, we're not going to be using it, so we just ignore it. The next one is the input to the function, the input data, which remember is a Python bytes-like object. Now, just for completeness, we can actually process not just bytes-like objects, but also arrays, NumPy arrays, byte arrays, different types of objects that all expose something called the buffer interface. So that's basically a way of passing binary data to C code from Python code. So the Python C API gives us a nice function called pyObjectGetBuffer. We just call it on input data, and we pass it a view object. The view object is basically just a struct that has a pointer pointing to the memory location and the length. So this is basically boilerplate. You can just copy paste it in most contexts. If you really need to do something fancy, then you need to understand it a bit better. But for most contexts, this is good enough. So once we have the input data length and memory address, we calculate the required buffer size. So remember, base64 takes 3 input bytes and turns it into 4 input bytes. So it's 4/3 of the input. Of course, if the input is not a multiple of 3, then you take the next largest multiple of 3 and take 4/3 of that. Okay, so that gives us the size. And now here there's a small trick, performance trick that we use. So remember, we want to output a Python bytes object. Now the naive way of doing this would be to use malloc to create a output buffer in C, and then use that output buffer to finally create the Python bytes object. But that has an extra copy because we are outputting to a different buffer, and then we are finally creating the bytes object from it. So we'll use a little trick, little known trick to avoid that. We'll first create our bytes object of the required size. Remember, the size is an upper bound. It's not an exact size because of the problem of input not being a multiple of 3. So we'll create the pybytes object from the required size. And once we have that, we'll call our simd base64 function with the input, which is the view object. The buff is a pointer to the input buffer and its length. And this Python C API function gives us the pointer to the underlying storage of the bytes object. And we pass it our size. And the base64 encode function will do its magic, and it will output the actual number of bytes it used in the output buffer. And so here's where the trick comes in. We call this Python C API function called pybytes resize. Now you note that its name starts with an underscore. It's a naughty function. You're not supposed to use it, but it's really useful. It helps you avoid a copy. So like if this was 1 GB of input data, you're avoiding a 1 GB copy. So what pybytes resize does is it simply adjusts the internal size field of the pybytes object to the new size, assuming the new size is less than the original size it was created with, which we know it is because we calculated an upper bound. So with this function, we resize our bytes object to the correct size and return it to Python. But benchmarking this function, it's amazing. It's 20 times as fast as the native base64 executable or the standard library base64 function. Now, a factor of 20 improvement is huge if your application happens to be constrained by base64 encoding. Then this would completely solve that. So we are, on my laptop, we are up to a rate of 21.5 gigabytes per second. And as you can see, it's a really simple function. There really isn't a lot of scope for bugs in this wrapper function. There is, of course, scope for bugs in the base64 encode implementation, but then for that matter, the Python interpreter itself is written in C, so if you trust that, you have to trust C code anyway. Okay. I lied a little bit. It's not just those 15 lines of code. We need a little bit more boilerplate to make our function available to Python. So Python fundamentally works with modules. Modules are kind of like namespaces where you collect classes and functions. So we need to create a module object in C and add our function to it. So there's a convention that the Python runtime uses to load modules. You call the initialization function of the module pyinit underscore and then some name of the module. So we'll name our module fastbase64 and we'll call this function pyinit base64. So when this C code is loaded dynamically by the interpreter using dlopen, it looks for this function and it executes it in order to initialize the module. So most of this is boilerplate. You can again copy paste it between different modules. There's a lot of depth and detail here that I'm not going to go into, but this is sort of the simplest basic module you can create. So the first sort of non-boilerplatey part is we need to give our previously created function pybase64, which is a wrapper function of the underlying simd library, a name that makes it available to Python. And the name we choose is b64enc. It doesn't matter, you can choose any name. I just chose that because it's short and easy to type. The third parameter there tells the Python runtime that this function of ours, pybase64, accepts only one input argument. Then there's a little bit more boilerplate, which I'm not going to go into. But you just, the important parts are you set the name of your module, again, fastbase64 matching that, and you tell it what functions your module has, which is defined up here. And that's it. With just these 15 lines of code, you create your Python module. And in your Python code, you can do from fastbase64 import b64enc and use it to process your data. There's also, of course, the question of building these modules. And some of you might know building C code is not easy, but I'm not going to go into that here. It's a challenge, but it's a challenge that is eminently manageable. Okay. So again, I'm motivating here why you should write your own C code. So there's an observation that in the Python standard library, there's no way to do streaming base64 encoding. Now, what is streaming base64 encoding? Imagine your input data is coming over a network or some other pipe, and it's coming in variable size chunks. So suppose your first input chunk is 5 bytes long. So your base64 encoder happily takes the first 3 bytes and outputs 4 bytes of data. But then what does it do with the trailing 2 bytes? It needs to wait for the next input chunk, prepend those trailing bytes to the start of that chunk, and then process it. So that's streaming encoding, when you get your data in irregular chunks. So the Python standard library actually doesn't have an API, at least as far as I know, to do streaming base64 encoding. But our nice base64 simd library has an API for doing it. And so let's wrap that API and make it available to Python. Now, to do streaming base64 encoding, we need to store some state, right? If you have 5 bytes and you process 3 of them, you're left over with those 2 bytes, and you need to store them until the next chunk arrives. So the way you do that in an object-oriented programming language is you create a class, you create objects. So you do that in Python. We create a class called streaming encoder. Now the streaming encoder is just a simple wrapper around the underlying base64 library state object. We don't care about that, but we just need to wrap it. There's some boilerplate there involved in creating the class, which is again common to most class definitions. Now remember, this is a class object we're creating in C, not in Python. So in Python, you write the class keyword and the name of the class and then define it. Here you create a struct. Now we need to define the methods for our streaming encoder class. And the first obvious method is encode, which takes the input object and outputs encoded byte object. So now the self is actually important. Self is a reference to our streaming encoder object. And we use it when we call the underlying library's encode function. We pass the state object to that function. So the rest of the code is the same as before, and It's just that we call the streaming encoding interface of the underlying library. So that's simple enough. Then we need one more function. So we need to tell our encoder when our input is finished. So then it can output some padding bytes if there are leftover bytes waiting from the last processed input chunk. So that's a really simple function. It just takes a reference to self again and args. Args here is unused because there are no arguments to this function. It's just telling the encoder that encoding is finished. Now we know that the final chunk from the encoder can be no larger than 4 bytes because output is always in 4-byte chunks. So we just use a fixed size array to write the output, and from that we create our PyBytes object, and that's it. That's just 2 functions we needed for our streaming encoder, and our streaming encoder is done. Now I'll just show you the boilerplate that's involved in making this streaming encoder class available to Python. Remember in the previous slides we saw how to make functions available to Python, but in this case we are creating an actual class which is a little more complicated, so we need a little more boilerplate. So the function for that is called exec module. And you can see that we are creating an encoder type. You can think of this as the class definition. And it has a whole bunch of boilerplate, which is, again, common between most Python type objects created in C. The important parts are, again, the name, which is the module name fastbase64, and the class name streaming encoder. So in our Python code, we will be using the name streaming encoder. And we tell Python that it has 2 methods, and we pass references to those 2 methods. The encode method takes 1 argument, and the finish method takes no arguments. That's it. That's all we need. With this function, we can add this class, streaming encoder, to our fastbase64 module. There's one more detail, which is when we're initializing the module, we pass it some slots. And so in that, we pass the exec module function, so that Python knows that when it's initializing the module after it has created the module object, it needs to call this exec module function to finish setting up the module. That's it, and this is again boilerplate. It will be common between most such extensions. So that's it. This shows that with just a little bit of boilerplate, we can achieve a 20x speed up of our Python code. And obviously, base64 is a bit of a contrived example. It's unlikely to be a performance bottleneck in most real-world scenarios. But in real-world scenarios, this can actually matter. And in fact, in my personal real-world scenario, it mattered because terminal escape codes, like for the Kitty terminal, actually have data encoded in base64. You can have image data embedded in an escape code encoded in base64. And it's important that that encoding and decoding is done as fast as possible. Okay, so that's enough for base64. Let's go to another real-world example. And let me reassure you, there's going to be no more code. This is just going to be talking points. It's going to illustrate, another use case of writing things in C. So the use case is HTML5 parsing. Now, as you all probably know, HTML is the basis of the web. There's an HTML5 standard, and this is actually some 1,500 pages long. It's full of corner cases and special handling, and not going into the details of that. Writing a parser for it is obviously a highly non-trivial task. Now the Python ecosystem, which is generally awesome, has an awesome library for this already. It's called HTML5lib. It's a library I use myself for many years. But it handles this full spec, and it has thousands of test cases. It's very robust. It's well made. I highly recommend this library. I have nothing bad to say about this library, except it's a little slow because it's pure Python. It parses, so as a benchmark, I tried parsing the HTML5 spec itself, and it parses the HTML5 spec at a speed of 1 megabyte per second. That's pretty slow. So in one of my applications, Calibre, a lot of its time is spent parsing HTML because it deals with ebooks, and ebooks are internally HTML. So I wanted to speed this up as much as I could. Now it's how much better can we do? It's important to realize that this problem is not like base64. Base64, you had an input as a bag of bytes and you output another bag of bytes. Here, with HTML5 parsing, what you want is your input is the HTML text, and you don't want to output HTML text again. You want to output some kind of object structure so that your program can actually do something with HTML, extract data, transform it, whatever. So now, because we are going to write that program in Python, our object structure needs to be in Python. And that sort of brings some limitations with it. Creating Python objects is slow. Each one has to be created on the heap. It needs a separate memory allocation. So we can't expect the kind of speed up we have in base 64. We're not going to reach gigabyte speeds here. But we can do significantly better than HTML5 lib. So there is one trick we can use, and that's an efficient object representation. So like I said, creating Python objects is slow, so you don't want your parser to create a full tree of Python objects right, on the outside. Instead, what you would like to do is parse the thing, represent it internally as a tree of C structs. In fact, the tree can even avoid most memory allocation by referring to the input data for its internal structures. But okay, that's the thing. And so what we want, the trick is that we'll create this tree, and it won't have a pre-built Python object representation. Instead, it will dynamically create the objects as they are needed. So often, when you are doing some manipulation on an HTML tree, you say want to find a particular tag with a particular ID. So you can just use an API to search for that in the tree, and then when a match is found, only then is the Python object for that tag created. So that greatly improves, mitigates the cost of creating a tree in Python. So now, thankfully, there's already a nice library in the Python ecosystem that does this. It's called LXML, and it's based on the C open source libxml2 library. It basically wraps libxml2 and presents a dynamically created object tree to the Python code that uses LXML. So I didn't have to write this full thing myself. I just used the LXML package. But the problem with the LXML package is that, at least at the time, it didn't have an HTML5 parser. You could hook it up with HTML5 lib, but then because HTML5 lib is pure Python, the end result is still slow. So what I did is I looked around for an existing C HTML5 parser because I didn't want to write that, parsing code myself. It's 1,500 pages long, the spec. So I found something called Gumbo, which is an HTML5 parser written by an ex-Google employee. And it was tested on 2 billion pages from Google's web cache. It's well written, it's robust. It handles most of HTML5. I had to make some improvements and modifications to it, but relatively minor things. And so my task was basically to link up Gumbo and LXML. I wanted to feed the HTML5 to Gumbo and have it, it will generate a parse tree, and I want to translate that parse tree into an LXML parse tree without involving Python anywhere in the process. So I did that, and the project is called HTML5 Parser. It's available on GitHub, and you can use it in your own code if you need fast HTML parsing. It took only about 1,000 lines of C. And so again, this is where I'm emphasizing the point that you can speed up your Python code with relatively small amounts of C. Like 1,000 lines of C is extremely manageable, auditable, maintainable, robust. I mean, there hasn't been a single bug against HTML5 parser in years. So what's the performance? That's the key. We want to make things faster. And if you benchmark it against the HTML5 spec, you'll get a 30 times speed up roughly. And so as you can see here, again, you have, like in base 64, we had a 20x speed up. Here you have a 30x speed up. And so this really makes a difference if HTML5 parsing is something you need, is a bottleneck in your application. And again, with just 1,000 lines of C, easily maintainable, easily written, easily audited and used. Okay, so that's it for the optimization use cases. Now, before I go on, let me say that premature optimization is the root of all evil. This is a famous saying. And the point here is that optimizing is hard. It takes hard work. You have to rewrite things in C. You have to identify better algorithms. Sometimes the end result is code that has some downsides. It's less maintainable. It requires you to use a native compiler, blah, blah, blah. So before optimizing, you should first make sure you really need to optimize. And how do we do that? Of course, the first thing is you notice your application is running slow. But once you notice that, then how do you decide what you want to optimize? So the Python standard library has a nice module called C profile. It allows you to profile your Python program. It's really easy to use. In your Python code, you simply import it, and then you call its run method with the name of the function you want to profile. And it will output a table of all the sub-functions that the function you're profiling calls and how long each function takes and so on. And you can use that profile data to decide what you need to optimize. So the obvious first criteria is you optimize code that is in the hot path, that is taking up most of the time, that is called a lot, that is critical. But the second, slightly more subtle point when you're deciding what to optimize in Python projects especially is code that has a nice data boundary. Now, what do I mean by that? So, as you program more and more, you'll sort of come to the realization that programs are really all about moving data. They take input data, they perform some transformations on them, and they output that data in some form. It could be as pixels on a screen, it could be as another bag of bytes, whatever. But basically, programs are data transformation machines. So now what we want to do is speed up our data transformation machine. And so we need to find parts of that machine that work on well-defined data boundaries. So for example, base 64 takes arbitrary bytes as input, but that's just a Python bytes object, and it outputs another Python bytes object. So that's a good boundary. We can implement that transformation from one bytes object to another as a black box. It doesn't matter what's in that black box. What matters is the input and the output. So that's a good data boundary. Similarly, HTML5 parsing, as input, you have HTML text. As output, you have a tree representing that text. It doesn't matter how the tree was generated. All that matters is that the tree is an accurate representation of the input. So that's another good data boundary. So you look for these kind of data boundaries. So like in Python programs, you'll have functions that call a lot of other Python functions, that in turn call a lot of other sub-functions, and then there's a whole tree of things. So you need to find some part in that tree that can be pruned. And that's kind of a skill you develop with practice. So let's look at a real world example. So some years ago, users were reporting in one of my projects, the Calibre project, that certain ebooks were very slow to open. So the first time Calibre opens an ebook, it does some pre-processing on the ebook's internal data to make it suitable for viewing. And that's cached, but it happens the first time you open the ebook. And for certain ebooks, this processing was taking up to minutes, which is completely unacceptable. Ideally, I would like to open most ebooks in about a second, but some ebooks were taking a minute. So I asked users to give me some examples, and I rewrote the code in Calibre so that to make it easily profilable. So what that means is you create a single entry point, and the code was multi-threaded, but I made it single-threaded optionally so I could profile it better. Okay, so after doing that, I ran the profiling. And this is kind of what the output of the Python C profile module looks like. I've cleaned it up a little. It's a little more noisy in reality, but it's basically like this. So the first most important line tells you how long it took, the task. It took 6 seconds here. Now the actual value is not important because the profiling module adds overhead. So in production, in real code, it won't actually take 6 seconds, but for purposes of optimization, we can use it as a baseline to compare. So we see that we have about 2 million function calls. These are Python function calls, and they execute in 6 seconds. So let's kind of look for our candidates for optimization in these functions. So I've output about the first 10 such functions. Each column, the first column is the number of times the function is called. Second column is the cumulative time, which is the total time that this function, that executing this function took, including all its calls. And there's a per call time, which is the time it takes per individual, average time it takes per individual call of the function. So the first function is just render, which is sort of the overall orchestrating function. It calls all the other sub-functions that do the actual work. So we don't want to optimize this because it doesn't have a good data boundary, and we basically have to rewrite everything from Python to C if you were doing a C-based optimization. So this is not a good candidate. So then let's look at the next candidate. The intervening ones are also orchestrating functions, basically. So the first such candidate looks like transform style sheet. So style sheet here refers to CSS styling in the ebook, and there are 2 calls to it, not 1, and that's presumably because this ebook that I'm profiling had 2 style sheets. So now transforming style sheets is a well-defined data boundary. It takes CSS text as input and output CSS text as output. It doesn't matter how it's implemented. And we see that from the cumulative time column, it takes 3 seconds, which is roughly half of the total time. So it looks like a good candidate for optimization. And indeed, when I looked at the samples that were pathological, it was because they had a lot of CSS text, much more than the average ebook. So if you look further down the table, you'll see more evidence that CSS is taking up a lot of time. So there's this parse CSS token, which is obviously parsing one piece of CSS, and it's called thousands of times, and it takes a lot of cumulative time. So we can conclude that there are more CSS functions in the profile. We can conclude that CSS parsing is our first port of call. It's the culprit. It's what we first try to optimize. Now, obviously, writing a CSS parser is not a trivial task. But it turns out that we can be smart. So I noticed that the rendering code in Calibre didn't actually need a full CSS parser. All it was doing is taking some CSS properties and transforming them. For example, URLs were made relative, font sizes were changed from absolute units to relative units, and so on. So all it really needed to do was recognize properties in the CSS style sheet and transform a handful of them. So I don't need to understand all the CSS spec. I don't need to write a full CSS parser. All I need to do is write enough of a parser that I can robustly transform some handful of CSS properties. And it turns out that that's easy to do. CSS is fairly well structured, and it took about 1,000 lines of C++ this time. I don't actually recall why I chose C++ for this, but I mean, it wouldn't, it's irrelevant. Okay, so with that, rewriting this CSS transformation, this transform style sheet function in native code, 1,000 lines of it, which is again a very reasonable amount of code. What is the result? So we look at our updated profile with our new accelerated code, and you can immediately see first that the number of Python function calls is halved from 2 million to 1 million. The time is also halved from 5.8 to 2.6 seconds. And now if you look at the process table, there's no CSS, at the profile table, there's no CSS functions in there. So we've completely eliminated CSS transformation as a source of slowness in our program. So now what else can we do? So if you look at this, we notice that the worst simple function is entity to Unicode, and it's called 50,000 times, and it uses a lot of cumulative time. We see also in that profile that there's a parsing of HTML now. Now I just told you about HTML5 parser, which this code uses and how fast it is. So it's kind of surprising that there's HTML in this profile. So why is that? And the reason was very simple. While the HTML parsing itself was fast, before parsing, for reasons I won't go into, Calibre would convert all the HTML entities into Unicode code points. And that's what you see here, this entity to Unicode function, and it's implemented in Python, and it's called 50,000 times. And it uses a regular expression to do the job. You can see that in the profile, there's the regular expression module being called. So with just the CSS rewrite, we've got a 2x speed up in this. And in the pathological cases that I was telling you about, there's a 60x speed up. But we can do better. We want to get down to 1 second. So the answer to that is to rewrite entity to Unicode in C. And that's really easy to do. An HTML entity is simply the ampersand character followed by either the entity name or a number, which is a Unicode code point. So what you do is you use our old friend SIMD to find these ampersand characters in the input fast in parallel. Once you found one, you pass the next few bytes. You convert the name, look up the name, or you convert the number directly into a Unicode code point, and you output that. So that's really easy to implement. But there's one more trick that I'll just briefly mention called perfect hashing. So now I'm sure all of you are familiar with Python dicts. They're basically hash tables. What a hash table does is it associates a key with a value. And the way it works is that it calculates a hash of the key, which is an integer essentially. It arranges those hashes in an array. Now the problem with a hash table is there can be collisions. So two keys that are not equal can hash to the same integer. In that case, the lookup for the hash table becomes a bit slower. But when you have a limited set of keys, like here we have the HTML entity names, which is a well-defined set of about 3,000 names in the HTML5 spec, we can do perfect hashing. We can generate a hash table, a hash function that never has any collisions on our input set. And there's a nice Linux tool called gperf, which does just that. It generates C code, which implements the perfect hash table for us, given a list of names. So I use that, and in addition, I had to write 200 lines of C to integrate it with Python and implement the simd lookup. And that's it. And with that optimization, we can see we are back. We're down to 1 second almost, which is kind of my target to start with. And we can see that in the profile, there is no individual function that's taking a lot of time. These are all sort of split between different functions that perform tasks. So there's no glaring function to optimize here. So that's a further 50% speed up for a total of a 4x speed up over the initial time of pre-processing the ebook. And remember, this is for an average ebook. For pathological cases, the speed up is much larger. Okay, so that's that. Now, I don't think I have time for this, but I have a few slides that would explain how you use simd to do some tasks like looking up bytes and base64 encoding. So catch me at some, at one of the breaks or something if you're interested. It's kind of fun, but I'll skip it for now. Okay, so last slide, you're almost done with me. The key takeaways from my talk, which I hope that you will take with you, is that Python programs can be very fast. They can be best in class, even though they're written mainly in Python. You just need to find the optimization, the code that needs to be optimized, and optimize the hell out of it. So how you do that, you profile, you identify functions in your code that are slow and that have good data boundaries, and then you optimize those. First, you look for pure Python opportunities. It could be that in your use case, just a pure Python optimization is enough. So use tricks like avoiding copies, use memory view, et cetera, et cetera. If you just Google, there are hundreds of blog posts about how you can optimize pure Python code. So I've just talked about a couple of tricks of that here. Finally, the most important thing, the key takeaway that I want you to take from this talk is don't be afraid of C. Use C when you can, learn it. It doesn't have to be C, it can be Rust, it can be C++, whatever. But you learn some native language. It's a really useful skill. It'll make you the go-to person in your organization or your project when people need performance, and you will be really valued and appreciated for it. So thank you for listening, and I hope I've communicated that it's worth optimizing your Python programs. So the slides are available online at that URL, and the benchmark code I use for benchmarking the base64 is also available if anyone is interested. So thank you. If any of you have questions.